All right, everyone. So David Wells, as a research scientist from UNC, he's actually been coming to these for a while. He showed up yesterday in his Atlanta version of the shirt for the conference. So it's great to have him back. He's going to talk to us about IBAMR today. So David, take it away.
All right, thank you. And thank you for having me here. So this is actually IBAMR talk 2 out of 3. Alex talked about IBAMR yesterday, and Boyce is talking about it this afternoon. So since I work with Boyce at UNC, I'm going to let Boyce talk a little bit more about our amazing results, and I'm going to focus a little bit more on the scientific software side of things. All right. So first, I want to list some of my collaborators, people who are doing really good work. These are mostly graduate students here at UNC. A few people have since graduated. Larissa, who is now at Align Technologies. Bryn, who splits her time between Lawrence Berkeley and UNC. Cole, who will be at Fordham, I think, starting this August, right? Yeah, so he's graduating. Marshall was a grad student. Now he's a postdoc with us. Boyce, of course. Charles is now at the University of Houston. Amneat, special shout out to Amneat. I feel like his students are the ones driving a lot of new features to IBAMR. It's unfortunate that they're not here, but they do a lot of important work. And as you may or may not know, I'm also one of the principal DL2 developers. A very special thanks goes to Peter, who in 2020, when he had a lot of time on his hands, worked like 70 hours a week to finally make tetrahedra happen in DL2. And a lot of what I do would not be possible if Peter had not somehow plunged through that stuff over the course of the last 5 years. So background and what I'm going to talk about. So why use PETSc? I think it's, at least as a DL2 person, I always find it fascinating to learn like what people actually like about DL2. So hopefully, I think even though it's maybe kind of basic, you might find it interesting to learn about some of the reasons that I use PETSc. I'll talk about the relevant equations. I'm going to focus a little bit less on the results, but I will talk about fluid structure interaction and the algorithms that we use. I'm going to talk about where specifically we use PETSc and then some future work. So please help me figure out how to use PC patch to do implicit IB time stepping. Definitely high on the to-do list. So goals of this talk. I really liked Alex's scale yesterday. I actually edited some of these slides to account for that last night. So I am very far to the left on doing HPC software and applied math, a lot less applications. I let the really biomechanics people at UNC really tell me what to do, and then I just kind of do it. So in my opinion, I succeed when people do cool stuff with my software. I think that's similarity between IBAMR, PETSc, and DL2. Like people who I've never talked to actually use our stuff and publish papers, which is always really great. And so in this talk in particular, I feel like I'll have succeeded if I run out of time instead of slides. So if you want to start arguing with me, or if you have questions, just please yell them out. If I can't answer them, Boyce probably can. It's good that I have him here to back me up. Okay, so motivation for a lot of this work. As you may or may not know, the IB method, or at least the formalization of the IB method that we use, came out of Charlie Peskin's group at NYU. And this is originally to do these biomechanical problems with heart valves and hearts. So as you may or may not know, heart disease is the #1 killer of Americans, and this is a chronic disease, and there's a lot of stuff that you can do to alleviate it in some way or another. There's something like 300,000 valve replacement surgeries per year, and one of the cool things about working at UNC is we actually get to talk to people doing valve replacement surgery, and it's really fun to actually get to collaborate with surgeons instead of just doing hypothetical work that might benefit them someday. We can actually talk to them and learn about what they're working with. And so part of what we need to do on our side of things is have just accurate simulations of the full cardiac cycle, which is a really difficult thing to do. And so we've accomplished that somehow. It took several years of work. And there's a bunch of other cool add-ons that happened recently. Larissa Abdullah, who recently graduated from UNC, was able to add electrophysiology into this to actually have like an electrical component driving the mechanics. Parallel scalability, always a problem that we have with the IB method. There's a lot of moving parts in these multi-physics problems to get correct. And so we have also an ongoing project at UNC called Cardinal to get students to write plugins instead of just these 500,000 line monoliths that are, I think most people probably have some experience with this. A student writes 5,000 lines of code, and that becomes this kind of inherited thing that gets tweaked and not all that well maintained. All right, so the underlying physics that I'm really concerned about with IBAMR is the Navier-Stokes equations, which I'm going to solve with finite differences on a Cartesian grid. And for the solid mechanics parts, which in here I have 2 heart valves in gold and some papillary muscles also in gold connected by the chordae, is finite strain elasticity. And that I'm going to model with a finite element method on an unstructured mesh. So in IBAMR, we typically use lib mesh. We also, over the last couple of years, have switched to DL2 just to, I feel like maybe if I was better with lib mesh, I know how to solve some of these problems. So I'm a DL2 person. And DL2 just has some better scaling capabilities in places that we need them. And so these 2 discretizations, finite elements for structural mechanics, pretty common. Finite differences for fluid mechanics, also pretty common, are coupled with the IB method. So a glossary of some terms that I'm going to use today. I'm going to try to be consistent in this because there's a lot of jargon. So IBAMR, Immersed-Boundary for Adaptive Mesh Refinement, is a software package at UNC with collaborators all over the place. DL2, Differential Equations Analysis Library version 2. It's kind of funny to write that one on version 9.6, but whatever. I didn't pick the name. So I'm going to try and be consistent when I say cell and refer to cells of the Cartesian grid, and that's something that's managed by Samurai, which is a package from Lawrence Livermore. And those cells go in things called patches. So when I talk about a patch, that's not the same as a PC patch. That's a giant patch of Cartesian grid cells. And an element is going to be a finite element. And finally, these things are coupled at quadrature points. It's just something you get when you do numerical integration. Okay, so what is great about PETSc? So I actually got this screenshot from the DL2 GitHub page yesterday. I think what's really great about PETSc is that like a VEC is still a VEC. I don't think I've ever had to do like a compatibility update to IBAMR in like the 8 years that I've been working on it. Like PETSc has changed a lot over the last 8 years, but our bindings haven't really changed. And I like trilinos. I use a lot of trilinos packages. I think that dialinos is what a graduate student called it once, and the name kind of stuck, is the main way people do parallel linear algebra with DL2. But as you may or may not know, trilinos is finally deprecating a lot of their packages, and we like don't have the developer power to actually fix this problem. It's a huge issue for us. So the fact that PETSc has a VEC as a VEC today and tomorrow and hopefully always, and that gets evolved, not just replaced at some point, is a really, really big deal for us. Similarly, installing stuff, always a huge problem. After answering too many emails, I wrote a giant script to install things for IBAMR users, and it uses basically, I guess, how many external packages? Quite a few that we just rely on build system. So the fact that build system is able to manage all this stuff for us is really, really helpful. And as you may or may not know, every time I upgrade my computer, Cython breaks, so I can't use PETSc for Pi. Sorry. And yeah, and I've never had serious compatibility problems with PETSc. I have had them with IBAMR when MPI communicator is unsigned int or other weird things. So a few things that I think PETSc does exceptionally well. I was amazed when you're looking through the CI that you can run like 11,000 tests in 20 minutes. For DL2, this would take like a day, maybe. It might take longer. And there's sort of this ineffable quality of PETSc where it's clearly written by people who agree on like a set of style guidelines and actually care about the work that they're doing, which is always nice to do. And yeah, it seems like the best advice that we have for using DL2 on a GPU right now, even though we have a lot of Cocos code ourselves, is just use VEC set type and mat set type. It works. It's really cool to watch that happen. All right, so as far as the relevant equations for IBAMR and the numerical discretizations I'm using, the first one is the Max scheme. It's an oldie but a goodie. I think many people in this room are familiar with it. I think, wow, it's been 60 years now. So the Max scheme, essentially, I don't know if my cursor is gonna, my cursor does kind of show up with some lag. So instead of a self-centered scheme, this is what's called the staggered discretization, if you haven't seen this before. Namely, I store the velocities of the fluid on the cell faces, which is kind of the midpoints of these squares that you see in this hex grid right here. And so this has a bunch of nice numerical features. It's difficult to extend to non-Cartesian geometries, but everything we do is structured block mesh refinement on the Eulerian side, so that's okay for us. And this tends to work, at least Boyce told me once, that it's about 10 to 100 times better at volume conservation for structures than just a cell-centered or node-centered scheme, which is really important for our application. And so one cool update that we have from the last time I gave some version of this talk is we actually know how to do this with, or we know how to get SPD Laplace operators now with the Max scheme. They're using Galerkin differences, something I worked on with Jeff Banks, if any of you know Jeff, many years ago. It's kind of work in progress, but it basically works, and we're hoping to publish something on it this year. That's mostly Bryn Barker's work. All right, so, oh, that can't be good. Why did that slide not go forward?
Oh, is it because of the moving the cursor off the...
Uh-oh.
Try moving just something around on your screen a little bit. Is it updated on your screen but not on the Zoom?
Yeah. That's strange.
Try going back and forth a little bit, or...
I had it happen to me yesterday where it lost exactly where I was. I just escaped out of full screen. Redid full screen.
I stopped sharing somehow, but it was still
Okay.
showing up.
Let's reshare.
That's fascinating. All right. Well, I shouldn't have clicked on anything. All right, did that work?
Let me check mine.
It says has started screen sharing, but I'm not seeing it.
Yeah, I'm not. Let's see. Yeah, I'm not seeing you with screen sharing. Is it just taking a while to share?
Unclear. That can't be good. Let me try this thing again.
Okay. Try
Oops.
sharing again.
For some reason, we're not seeing it.
Let me try. I can also just email you the slides if this takes more than a minute, but
We'll give it one more shot.
Yeah.
See.
wait, my slides are. One sec. Where do they go? Let's try.
Okay, it's showing up.
Yeah, it's showing up now.
All right. Sorry about that. All right, how much time do I have left?
I'm next. Don't worry. Take your time.
Oh.
Extra time.
Thanks. All right. Well, try to get through some of these other details a little bit more quickly. All right. So like I said, we focus on using structured adaptive mesh refinement, sometimes called SAMR, or now why is this thing up here? Go
Yeah, I
away.
think you can hit the far right, that little, yeah.
There we go. Thanks. And so, yeah, like I said, a really nice advantage of the IB method is that since we have these two completely different discretizations, we can just do all Cartesian grids for the fluid solve, which is really great. So we have these really fast optimized fluid solvers for this and finite elements where we need to use unstructured grids. All right, and so the other half of this is, again, here's a cutaway shot of the heart mesh that I think we ended up using in the 2024 paper with Marshall Davey. There's a lot of really interesting things going on in this heart mesh. I think that it has something like 100 different boundary IDs when you add them all up. There's dozens of side sets in Exodus 2 terminology, and some of them overlap with each other. And I think that we ended up with 9 active strain models and 25 different body forces or stresses defined on this thing. It was a really impressive set of just material models to lump into one equation to solve. And again, Larissa made it even more complicated by adding electrophysiology to this equation and actually solving this bidomain equation for propagating an electrical wave across the heart. Or was it monodomain? You remember, boys? Okay, it's monodomain. Sorry. Yeah, so if you want to know more about the actual results, come to Boyce's talk today. Yeah, so if you're not so familiar with FSI, this falls under the category of a partition scheme. Namely, I have one set of solvers for the fluid side, and I have one set of solvers for the mechanics side, and then I have some coupling method to make them talk to each other. And so the advantage of a partition method is code reuse, I think, is a big one. If you have a finite element solver you really like, you just have to learn how to make it talk to your fluid solver that you really like. And a really cool feature of that for us has been, we started with libmesh, then DL2 supported simplices, and now we use DL2 without actually needing to modify any code in IBAMR itself. We just wrote something on top of IBAMR. And so we can use different algorithms for different domains, but we do run into some problems with numerical instabilities. So I really like this picture. I've had it for a long time. I think this is a really good depiction of the added mass instability. So you can think that if you just had a styrofoam ball in outer space and you kind of flicked it, it would just fly off according to F is equal to ma. But if you flicked it and let's say it was in a tub of water, it would not go nearly as far because it would have to displace the water that was in front of it. And this is sometimes called the added mass instability, namely when you have this force acting on a solid, you have to actually take into account the fluid that is like pushed out of the way and entrained behind the structure as well. And so if you're doing something like, I don't know, an airplane, then the steel wing is just going to go wherever it wants to go. But when you have equal densities between your structure and your fluid, then this becomes a real source of instabilities. That's one reason techniques like the IB method were developed for neutrally buoyant flows, or neutrally buoyant structures, excuse me. So the way the Immersed-Boundary method works, again, when I say Immersed-Boundary method, there's more than one thing called the Immersed-Boundary method. This is the Charlie Peskin version, is we have an immersed method, meaning that we solve for the velocity at all points, including inside the structure. And unlike the normal FSI scheme you might use in aerospace engineering, here the structure velocity is given by the fluid velocity by just interpolating it everywhere. And also the thing is reversed from the standard scheme when it comes to forces. Forces are calculated by a force density on the structure and then spread onto the background grid. And both these operations are done by regularized delta functions. So this works with really hard geometries. Like even just creating this heart mesh was a multi-year adventure in just getting clinical data, trying to fix things to work around problems with geometries, CAD data, stuff like that. And so fortunately, we don't have to have a domain that's cut away from that. We just have our structural mesh, and that's all that we need to do here. So it works really well with hard geometries because the fluid solve is always on a Cartesian grid. And that's a bunch of really nice properties like conservation of force and torque. There are some disadvantages, like there's first-order convergence at structure boundaries. There are ways to fix this that we haven't quite finished yet. And yeah, coupling occurs across a volume instead of an interface, which also makes these coupling operators pretty expensive. But we've done a really good job, I think, over the last couple of years of optimizing that part of IBAMR. And in particular, we can couple things now with nodal quadrature instead of elemental quadrature. And nodal quadrature is always like an order of magnitude less work than doing this elemental coupling scheme. Okay, good. I thought I'd pause for a second. So yeah, I'm not going to go too much into detail on this. But if you haven't seen them before, these are the Navier-Stokes equations. So we're just solving the standard viscid Navier-Stokes equations with incompressibility. And the really key thing here, I'm kind of hesitant to click on this now, but I'll at least move the cursor towards it. The really key thing here is we use these delta functions here at a continuous level to just say, okay, the velocity of the structure is the velocity of the fluid just with this integral transformation. And same thing with the force. The force on the fluid is just the force on the structure also with an integral. And the force is defined weakly in this way. All right, so I think these pictures really help. This picture is an extremely exaggerated depiction of what happens when you put a triangle in 2D on a finite difference grid. Normally you want your elements to be about the same size as your cells. Here, this triangle is the size of like, I don't know, 15 cells. It's way too big. But it does also do a good job showing the coupling at quadrature points. So if you can see them, these black points here that are inside each of these blue boxes are quadrature points. And there's some, I guess, 9-point stencil applied to these to either interpolate a velocity or spread a force. And so, oh yeah, this is the velocity projection side. So this time it's interpolating a velocity. I have the same picture on the next slide for spreading a force. So the equations look something like this. And you end up either doing a mass matrix solve at the end of the day, which is pretty easy, or you end up just doing nothing if you have a nodal quadrature method, which is pretty cool. I think that kind of an odd feature of this is the only solves that you do with finite elements in this formulation end up being mass matrix solves, which is really nice. All the difficult linear solves are in the fluid equations. All right, so same thing for the forces. Here, you can think that a force is defined on the structural mesh, and it's applied to the background grid by the same B-spline, or not B-spline, the same IB kernels of some kind or another. And it looks something like this. All right, so where do we use PETSc? So I think to most people in this room, this list of parameters might look pretty familiar. It's really nice to be able to experiment with these things in practice and just try out like different velocity preconditioners, different velocity KSPs, tolerances, logging. It's all available through a nice command line interface. Same thing with KSP error if not converged, critical flag for when things tend to blow up quite frequently. So for us, IBAMR has a bunch of samurai wrappers, which are just, I don't know how many people in here have ever written their own VEC implementation, but it's actually pretty easy. You just have to I guess if you have a C++ program, you write a bunch of static functions, and then you just copy pointers to them into some array of pointers to member functions, and that's basically it. It's pretty easy to do. And we also have similar wrappers around KSP, MAT, and PC objects for actually getting everything done at once. It's kind of funny to give this presentation to Boyce, because Boyce is the person who wrote all of this. And yeah, so with fluid solves, I don't think we ever actually set up do we set up matrices, Boyce, ever? No. Yeah, so fluid solves are completely matrix-free. It's just a bunch of basically Fortran 77 loops over structured grid data, which is great. It's pretty performance stuff. And at the end of the day, pretty simple code to understand if you need to look at it. So for the force spreading, let's take a... Uh-oh, did this get out of sync again? That can't be good. I guess what confuses me the most is that it gets stuck. It doesn't just kick me out of this meeting.
Maybe just try a quick reconnect again.
Yeah. Let's try that.
No, same thing as last time.
Did that
For
work?
some reason, it doesn't want to screen share after a certain point.
Huh. I don't think I've ever had that happen to me in Zoom, but...
I was logged in for like 3 hours yesterday.
Well, for mine, it had a strange thing where mine stopped screen sharing after some point as well. So
I wonder if it has to do with the screensaver kicking in, because mine doesn't.
I don't think so, because I'm hitting the left and right arrows on this pretty frequently. Is that thing working?
Yeah.
Okay, great. Let me see. Yeah, let's try to finish this up. All right, so I guess the last part of this talk is I'm really going to talk about some details about how we use PETSc for some of these more interesting IB coupling operators. So there are the linear solvers, which I just showed about. What I think is more interesting is talking about how we can improve parallelization by just using a bunch of PETSc things. So if you look at the force spreading operator, this is kind of interesting. So I'm really a finite element person, more so than a finite difference person. And if you look at it kind of carefully, you'll note, okay, so these forces get spread into these Cartesian grid points from all the quadrature points, essentially, on your structure. So it's a little bit like how in finite elements, when you assemble a load vector, you might have one node that's shared by multiple elements, and they all have some contribution they have to add into them. It's kind of conceptually similar to this. And so what we can think is, if I know where all the quadrature points are, well, I know that this regularized delta function has some width of some number of cells. Therefore, I kind of know, if I know where all the quadrature points are, which cells they're going to interact with. So that's always a difficult parallel problem because, I mean, libmesh or GL2 has some idea about how to partition your data in parallel. Samurai has some completely different idea about how to partition everything in parallel. Getting them to talk to each other is kind of tricky. I'm not really going to talk about that today. But I'm going to talk about some of these algorithms in some detail. So kind of our prototype for how we got this done, which was really the original implementation, is, okay, well, if I just make my sort of bounding box around my patch large enough, I'm going to capture all the quadrature points, which could conceivably just contribute some value onto a Cartesian grid cell that I own here. And so that's a good start, and it guarantees that you don't like miss points, but it's also needlessly expensive for two reasons. So number one, I think I calculated this assigns like 25% more elements than like necessary. So you have to do, I guess, 33% more work, 75 to 100, when you loop across your cells. And number two, it makes it really difficult to load balance these things in parallel. Like there's some work associated with each quadrature point. And so, okay, if I know how many quadrature points are in a patch, I can say this patch has 500 work units. But you can't load balance based on ghost data that well. That's kind of a, like, who owns the ghost data? You can't say, okay, well, this is the amount of data or work in this ghost patch. Please make sure that this work that you don't own is somehow accounted for. It's really just too difficult to do in some sense. So the enhancement that we have is that instead of doing all the quadrature points which might interact with the patch, we just find all the quadrature points that are inside the patch and allow them to spread into ghost regions, which kind of looks like finite element assembly, where you have to do this reduction step at the end in parallel. And so this is implemented in the IBAMR class. And so some more computational details on how this works. So assumption of Samurai, or at least an assumption of the version of Samurai that we use, is that there's like O of number of processors patches. So in general, it's not like finite elements where you have to somehow partition all the elements globally. But the number of patches do have to be partitioned globally, but there's typically not that many of them. You might have like 3 or 4 per processor if you've done a good job chopping up the grid. So our problems aren't that large, so we just store all of them on every processor. Because it's in practice only a couple thousand patches. We're not running really large simulations. So it's relatively easy, because you already know where the patches are and which patches are yours, to just enumerate all the degrees of freedom and the ghost degrees of freedom on your finite difference grid. And also, you can enumerate your non-physical DOFs. So labeling those as -1s, really nice PETSc feature that I use. And so if you actually go through this bit of code, there's a really nice pathway with PETSc index sets to actually get out the local indices that you have and just fill up your vectors with just local indexing into arrays that you define, which is always faster than this global indexing just by the kind of normal thing. I don't know how many people are using IS global to local mapping apply, but it's kind of a critical function for me. And then it's just kind of the normal things with updating vector ghosts from local forms to just doing this parallel reduction where you sum into ghost regions, and those ghost regions have to be summed into their locally, or the processor that actually owns those degrees of freedom. All right, and then for velocity interpolation, again, mathematically it's the adjoint of spreading, so they have a lot of things in common. It's just kind of pointing the other way. I want to go from the Cartesian grid back to the finite element mesh. So for that, kind of the prototype is just ignore the problem. So libmesh, or at least the libmesh data structures that we were using, store all degrees of freedom on every processor. So if you have an element, you know which degrees of freedom are on it. And so this works. I really had a bunch of performance problems with vecstash for this reason. So vecstash is extremely convenient, but it also seems to have to reconstruct, because I guess the communication pattern can change every time. It has to kind of redo everything every time, which is not ideal. So kind of the enhanced version of this is that we already know the same, well, we know the global DOF ordering for libmesh. We just have to set up really big ghost regions. Because like a priori, I already know which patches I'm going to intersect, so I already know which quadrature points are relevant on the current processor. So I just add a giant ghost region to the vector that I'm working on, and then I sum into that ghost region instead of using vecstash, which works pretty well. And so the more enhanced version of this is something that we've written over the last couple of years, which just uses all DL2 stuff instead of these PETSc vectors managed by libmesh. And so that uses an approach pretty similar to vexscatter to just do completely local indexing. And this uses the DL2 class MPI partitioner, which is a lot like PETSc starforce / vexscatter, and then our own in-house scatter class. All right, so future work. I have 3 slides on this, and then I'm done. So one major problem that we have is this line here. The time steps that we have to use are tiny. That is 0.0000625 times dx, and then for some reason divided by 2 at the end. I just copied and pasted this out of an input file we used for Marshall's thesis. So there's a lot of numerical stiffness, particularly from the core day, we think, in modeling these things, and this is a big problem for us. Like these methods work, but the time step limitations are quite large. So this explicit treatment of forces is really convenient because it allows you to just like write down any old force that you have from some biomechanics paper. But it's also limited in the sense that when they become very stiff, or if you have things like steel, then your time step restrictions become quite severe. So Cole seems to have a good method to actually do implicit IB that seems to work for very stiff materials. And so we really want to get this in IBAMR sooner rather than later, which means figuring out how to use PC patch, which, like I was saying earlier, kind of surprisingly, PC patch seems to have no examples.
It's all of them are in Firedrake.
All of them are in Firedrake.
I wrote it with Patrick and Lawrence, and they wrote all the examples. So all the examples are Firedrake except for the ones that I needed to merge the MR for testing.
Huh. Well, that explains that. All right, so that is that. And then I guess the people haven't stopped me yet, so I'll go through the rest of my slides and then I'll be done. So we have this closed source for now until we figure out how to open source it package at UNC called Cardinal. And the kind of genesis of this is just noting that every student seems to write like, 5,000 lines of code, typically all in one giant main function. And this code tends to be pretty repetitive. like they have to do post-processing, they have to do statistics, they have to load their data in and out. And so frequently they also have to implement from literature like these electrical models or these material models. And a lot of like public versions, especially these like electrical models or like these models of neurons have just like bugs in them. Like they have like pretty obvious undefined behavior. It's kind of stunning actually like what the state of the art is here. Definitely something that can be improved upon by the community. So in addition to that, like, I mean, students need to learn how to do all this stuff, but like, it's also not a good use of their time to really write everything from scratch. So kind of our goal in this project is just to have a really, not a template project per se, but give them sort of a implementation of all the things that they need, and hopefully they only have to write like an input file or maybe a plugin to get the new physics or the new simulation they care about done. So what we have is our heart model is now just an input file for Cardinal, which is pretty cool. So that's how I was able to count that we use 9 active strain models and 25 forces. I just searched through the input file and counted them up. I'd be kind of curious to learn more about how people handle these things, because this is way past the point of being able to reasonably handle things with command line arguments. Like, I can't specify like 25 material models in command line arguments. I mean, I could, but like, it seems like a poor choice. So it'd be cool to learn about what people are doing here. And I guess another big PETSc question is, we now have one centralized logging facility for like statistical quantities. I don't know if there's something in PETSc that'll just like write a nested HDF5 file for me. Of course there is. What's it called?
There's low-level tools in the HDF5 viewer, and then there's higher-level tools in VEC that write VECs to their higher-level tools in DM that write structured groups of VECs and ISs to HDF5.
Okay.
And do you need it to be? Do you need parallelism? Like, do you need a consistent thing written out that's originally parallel that you want to go on?
I think the answer is no. I really just want to save like, here's like basically 10 numbers per time step. Here's like a bunch of flow rates or pressures. These aren't like vectors or matrices, they're just scalars.
When I do stuff like that, I tend to just write extensions to the logging system.
Huh.
So like PETSc log. So for instance, when we're writing MMS, I write the errors and the sizes as payloads of the logging functions. And then those get, then I can just query them out of the log files. And there's a CSV that works in parallel. And so I write a big CSV file. That way you get all the data from the various ranks and then canonicalized, and you can query them. So that's how like the performance analysis that's automated works. Al wrote that. So we could talk about it. That might be something interesting. There's also like the CREST, the rocket people that we work with. They write similar things to HDF5 by just putting them in a vector or IS viewing, and that'll view to HDF5, and you can manage the hierarchy by setting groups and stuff. And that worked well for them because they have a lot of experimental data that they also want to compare with. So they have a standard format where you write simulation data and experimental data in the same HDF5 format that you post-process with Python tools on top of that. And it works easy.
Yeah, it's always good to learn how other people do these things.
Rich? Go ahead, Richard.
I just have a comment on
Yeah?
your too many command line options. PETSc's got helper routines to let you import command line options like in a YAML file.
Oh.
It's a lot easier to, if you have a ton of them, to keep track of them that way.
I did not know PETSc supported YAML in that way. That's kind of cool.
That's what we use for the rocket thing too.
Okay. All right, well, this is my last slide, so.
All right, let's take a speaker. We already had a little bit of a back and forth session. Do we have any more questions? All right, David, thank you.
Sure.
So.